Now, conceptually, superposition is a fairly straightforward chapter. As a matter of fact, it's almost unfairly straightforward. If we look at different types of quantities that we've been exposed to so far, we have multiplication, we have two types of vector multiplication, the dot product or the inner product where you have, or the scalar product where vector times vector equals scalar. We have vector times vector equals vector, the vector or cross product, and yet if we have two waves, let's say each is a function of some, both traveling in the x direction. Let's say both is a function of x, just to make this as easy as possible, and both a function of time. Then the total displacement of both waves is only equal to the sum of those two waves. That is the easiest possible relationship we could hope for, and yet we end up with that. As a matter of fact, in order to make this section be worth any time at all, to make it worth your time to download, we'll need to do this as an example. So let's say that I've got one wave where I have the first wavelength is 40 centimeters, and the frequency is 6 hertz, and I've got a second wave that has a wavelength of 50 centimeters, and actually, let me make that a frequency of 2 hertz. Now, a couple more clues. Suppose we say that both waves have a displacement equal to 0 at the origin when the time's equal to 0. What this is telling us is that the phase shift of wave 1, well, because both waves have the same displacement, the phase at a particular point, the phase shift for both of those waves will be equal to each other. Because I've got both waves will have a displacement of 0 at x is equal and time is equal to 0, then I can say that the phase shifts are 0 if, and I could even use the longer mathematical if and only if, we use the displacement as some sine function. Now, let me toss in two other things that I've missed. Let's say that the amplitude of wave 1 is 4 centimeters. And the amplitude of wave 2 is, 8 centimeters. Then, if I want, let me back up just a little bit here. You can pause this, obviously, if you are panicking, oh, I'm about to erase something, so cool. I'll just move it, feel free to move as easily on that as I will. Suppose I want to know the displacement at x is equal to 12 centimeters and t is equal to 0.5 seconds. Notice throughout everything I've used here is good to 3 significant figures. That's kind of a common default. Sometimes I do not have to say, hey, be sure that you're still tracking significant figures while you're doing problems, because I'll do something sneaky on an assessment. I don't have to say that because mastering physics is extremely picky, as is good, about significant figures when you're entering things in. So commonly, we work with 3 significant figures because 5, 6, or 7 is merely excessive. That's just making you do more work. And yet, 1 or 2 significant figures we can lose some ideas about what's going on or some understanding of behavior just because we are rounding too much. Now, if I want that, then, okay, let me check to make sure I'm getting the right scale. Seems so. Then I can say the displacement at x is equal to 12 centimeters and, t is equal to 0.500 seconds is just equal to the sum of these 2 things together. So, 4 centimeters, the amplitude of thing A, times the sine of kx, which is, k is the wave number, that's 2 pi over lambda, which is 40 centimeters, times x, which is 12 centimeters. Minus omega, which is 2 pi times the frequency times the time plus 8 centimeters times the sine of the wave number for the second wave, k, which is 2 pi over lambda. Now you'll notice as I'm going through at 2 pi over 50 centimeters, that in this case, I did not bother to take the wavelength or the position and put it into standard units, like say meters. Because in this case, since I've had a bit of practice doing these, I know that, okay, the wave number is going to include 1 over units, and the distance will be units of distance. So, those 2, as long as they're in the same units, they'll cancel out. So 2 pi over 50 centimeters divided by 12 centimeters minus 2 pi times hertz or 1 over second. So hertz times seconds is unitless. 6 times 0.5 is 3. Oops. Foolish of me. I'm sorry. I should be copying this as it was before. I jumped into solving, which is not good. 2 pi times 2 hertz times 0.5 seconds. At this point, there'll be a couple of places in the class where the physics exist just as we're setting this material up. There comes a point where, like, right now the physics is done. Now, all that we have left is merely algebra. So, oh, and when you're doing this, remember, if you're doing this on a calculator, I like doing this on Excel. The reason why I do my math in Excel is because I can have each step in a separate box. So when something gets screwed up partway through, I can look back step by step and find out where things went wrong. If I'm just doing this on a calculator, I cannot do it. If I'm doing this on paper, I can go back and find out where things went wrong, but if I want to change something, then I've got to recreate everything from that point on. Whereas in Excel, I can just find out where I made my mistake, change it, and let it calculate things down. The reason why I paused for that warning is because when you're doing angles, the angles could be in degree mode, could be in radian mode. Those will give you drastically different answers. So you wish to be very, very careful when you're setting that up. Again, if this were a face-to-face class, there are times where people would say, hey, I just made this little mistake. Why did you not give me credit for that? And it's like, well, because sometimes you should look at this and say, visually, that should have been a warning to you. You know, there should have been something where if the calculation's like ridiculously away from where you expect it to be, you should notice those things. If you're doing this online course, then the program that you're using, for example, Mastering Physics or WebWork, won't accept it at all. So let me grab these numbers real quickly. Excel automatically starts in radians, so that gives me 2 pi times 12 divided by 40, and two pi times 6 times 0.5 let's see here. The second wave has a wavelength of 50 centimeters and a frequency of 2 hertz. So let me just calculate that out into this. Excel is being strangely stubborn. So, when you add these two together, and you'll be adding one 3 significant figure to another 3 significant figure in a way that will take this over 10 centimeters, and so you will get, this is the correct number of significant figures for the answer, but the answer should be 11.79 centimeters.